Percent yield is a remarkably simple calculation to do, but before we do that, we need to make sure we understand what is percent yield and why do we even bother calculating percent yield. So percent yield is basically a comparison. Gosh, my penmanship looks horrible on this. A comparison of our calculated answer and is acting funny versus experimental answer. I'm going to say experimental result. Let me just say it that way. I'm going to move this over here. Experimental result. Okay, so basically after we perform a chemical reaction, we want to have a good idea of just how successful or efficient a chemical reaction was. We want to say, okay, if this is what we expected to get, how much did we actually get from the real experiment in the real world? So to do that, we're going to compare what's called the theoretical. The theoretical is what we calculate. So when we do a calculation on a piece of paper, that is theoretical. We haven't actually done the experiment. We're just knowing using a calculator and a pencil and some paper as to what we should get, right? That is theoretically speaking, because again, we haven't done anything as far as an actual experiment. The actual yield is from the experiment itself. So after we do the experiment, we're going to react the reactants exactly the same way as what the reaction tells us to do. We're going to collect the product, we're going to weigh it, and we're going to determine how much do we actually get from the real world experiment. Then we're going to compare what we got from the real world experiment, which is the actual yield, and we're going to compare that to what we got on paper, which is the theoretical yield. We're going to compare those two, and then from that very simple calculation, we'll be able to determine what is the percent yield or how efficient was our reaction. So the reaction itself is quite simple. You'll see it's right here on your screen, right here. We basically take the actual, which again is from the experiment, divided by the theoretical, which again is from your calculation, multiply by 100, and you get a percentage. Now, what you need to know is that will always be less than 100%. You can never get a percent yield greater than 100% because in real world, what we get on paper, again, is if the reaction went 100% to completion, which is not actually possible. So what we're going to get for a percent yield is always 100% of the time going to be less than 100%. Okay, this has something to do with thermodynamics, and we'll get into more of this later. But basically, like for example, in this reaction right here, we have aluminum sulfide decomposing into aluminum and sulfur. Now, as it decomposes, you would think that all the aluminum sulfide would decompose, and we would be left with nothing but all aluminum and all sulfur. But that's not actually correct. At all times, we will still be left with a little bit aluminum sulfide. Therefore, our percent yield will have to be less than 100%. That again is a property of thermodynamics. And like I said, we'll get into that in much more detail later. Okay, so let's go ahead and look at number 11. Let's see if we could solve this problem and figure out the percent yield. So first thing I'm going to do is balance this equation. For every one of these, I'm going to need 2 aluminums and 3 sulfurs. Man, I wish every balancing was that easy, right? So what we're given is 2,100 grams of aluminum sulfide. It is decomposed according to the reaction, which is a decomposition reaction. And the actual yield of sulfur is 1,100 grams. So notice they're giving us this. We have 2,100 grams of this. And then they're saying the actual yield from the experiment came out to be this much of the product of sulfur. So we need to convert this into this and figure out how much theoretically we should be able to obtain according to our calculation, and then compare it to the actual yield, which again is 1,100 grams of sulfur. So that's what we're going to do here in this particular problem. We're going to solve for the same thing we're already given, which may sound silly, but I promise you our answer is not going to be 1,100. Again, it can't. It's going to have to be something actually larger because, again, remember our calculation, our theoretical is going to be larger than the actual, okay? So let's go ahead and start this out. So we're going to start with 2,100 grams of aluminum sulfide. Again, I'm going to go ahead and get out of grams of aluminum sulfide and convert that into moles of aluminum sulfide. Okay, this is where I'm going to change my compounds, right? So moles of aluminum sulfide needs to be canceled because we're going to get out of that compound and into the product that they already gave us, which is sulfur. But we don't want moles of sulfur because, again, remember, they're giving us grams. So we need to get out of moles of sulfur and into grams of sulfur. All right, as you guys know, whenever we have moles on top of grams or grams on top of moles, the moles is always 1, and the grams comes from the periodic table. So I'm going to add the mass of aluminum, which is 26.982. I'm going to multiply that by 2. And I'm going to add that to the mass of sulfur, which is 32.066. Multiply that by 3. And I'm going to add that together. And my molar mass of aluminum sulfide is 150.162. So that's the mass from the periodic table of aluminum sulfide. Now, on the other side, we have grams on top of moles. So, of course, the mole is going to be 1, and the grams comes from the periodic table. Since it's just, why did I blank out? Since it's just sulfur, again, it's just going to be 32.066. All right, in the middle step, when we have moles on top of moles, again, you guys should all know this by now, this comes from, of course, the balanced chemical equation. Moles of aluminum sulfide is right here. Again, that's going to be 1. Moles of sulfur is right there. That's going to be a 3. All right, now I just need to get my calculator and figure out what the answer is. This will cancel. This will cancel. That will cancel. Oops, I erased my 3, didn't I? That's a 3. My apologies. And so we're going to be left with some amount of grams of sulfur. Okay, so I'm going to take my calculator. I'm going to put 2100 times 1 times 3 times 32.066 divided by 150.162 divided by 1 equals, and that comes out to be 1,345.319 grams of sulfur. All right, so that is the theoretical, meaning in a perfect world, if 100% of the reactants did decompose into aluminum and sulfur, we should be left with 1,345.319 grams of sulfur. But remember, in the real world, it doesn't work like that. So what we're going to need to do now is the actual, percent yield problem. So everything we've done so far, remember, is a review. Nothing here is new. What we're going to do now is the only new part, which is the actual percent yield formula. So again, notice right here is the equation. So we're going to take our actual yield, which is from the question. We were given 1,100 grams of sulfur was produced experimentally. We theoretically say that we should be able to get 1,345 grams, 0.319 grams of sulfur. I'm going to multiply those by 100 to get it into a percentage. I'm going to get my calculator. 1,100 divided by 1,345.319 times 100 equals, and my final percent yield is 81.765%. There's our answer. So that means we, again, relative to our calculated number, which is, again, in that maroon color, the real experimental data, which was 1,100 grams, represents about almost 82% of the theoretical, which honestly, in the real world, if you're working at a real formulation chemistry lab, that's actually not that bad. I could hold my head high and tell my boss or whoever that an almost 82% yield, that's not too bad. Like I said, anything maybe 60, 50, that's not so good. Might need to tweak your experiment a little bit. But again, we're not going to get very likely into the 90s and definitely not 100 or above. All right, guys, that's percent yield. Again, it's just a comparison to see what is the experimental, remember, which is called the actual, versus what you calculate, which is called the theoretical. Then we just basically do a very simple calculation to see, again, how efficient and how thorough was our chemical reaction. As always, guys, thanks for watching.